Hello, in this video we're going to go over the second fundamental theorem of calculus. First, we are going to talk about the mean value theorem for integrals. First of all, what is the mean value theorem integrals and what's the intuition behind it? If you look at the a function, continuous function from a to b, the area underneath the graph of this function is the integral from a to b of f. If you want to find the average value of the function, average value of a function is the value that if you replace that if you replace all of the values of the function by that value, the area underneath the graph of the function remains the same. So let me give you an example, so hopefully that makes sense. If you look at these numbers, let's say you look at a class and the class scores are 70, 80, 85, 85, and 90. And the question is, what's the average score in this class? So what is the average score in this class? It is a number that if you replace all of these scores by that same number, then the total score would not be different. So in other words, 5x, if you replace each one of these by x, is going to be the sum of these numbers, 70, 80, 85 twice, and 90. So the average score would be the sum of all the scores, whatever that might be, divided by 5. Now, average value of a function has a similar interpretation. So if you have a function y equals f of x, the average value is a number that if you replace all of the values of the function by that number, the area underneath the graph would not change. So it looks like maybe it has to be a little bit lower. So it's a number that the area underneath the graph is going to be the same for this constant and the function f. So if you look at the area underneath the graph, the area underneath the graph is integral from a to b of f. That must be the same as this average value, which I will call c, times the base. So c times b minus a. So this average value c is 1 over b minus a times the integral from a to b of f. So the average value of the function is defined as 1 over b minus a times the integral from a to b of f. Okay, so now what does this theorem tell us and how do we prove that? So this theorem tells us which is called the mean value theorem for integrals. It tells us that average value of a function that is continuous is a functional value. In other words, if f from closed interval a b to r is continuous, then there is some x naught between a and b that 1 over b minus a times the integral from a to b of f is equal to the value of the function at that point. In other words, average value is equal to a functional value. If I want to show that some equality, some equation has a solution, I will have to use IVT. So I will have to show this quantity is a functional value. So in other words, something is more than this quantity and some functional value is less than this quantity. So what would be more than this quantity? It would have to be the maximum of the function. What would be less than this quantity? It would have to be the minimum of the function. So we're going to go ahead and do that. By the extreme value theorem, f attains its max and mean over the interval from a to b. Suppose x sub lowercase m and x sub capital M are minimizer and maximizer of f respectively. So that means f of x, if x sub lowercase m is less than or equal to f of x less than or equal to f of x sub capital M for all x. Now we can take the integral of both sides. Integral from a to b of f of x sub lowercase m is less than or equal to integral from a to b of f less than or equal to integral from a to b of f x sub capital M by the monotonicity. So we know the integral of a constant. So integral of a constant would be f of x sub capital lowercase m times b minus a. That's less than or equal to integral from a to b of f less than or equal to f of x sub capital M b minus a. We are going to multiply both, divide both sides by all sides by b minus a. We get f of x sub lowercase m less than or equal to 1 over b minus a integral from a to b of f less than or equal to f of x sub capital M. So that means the value 1 over b minus a times integral of f from a to b is between two functional values. So since f is continuous by the intermediate value theorem, there is some c, or I guess they called it x naught, inside the interval ab. In fact, it's inside the interval from xm to xm, x lowercase m to x capital M, or x capital M to x lowercase m, depending on which one is smaller, such that f of x naught is equal to this average value. And that's exactly what we wanted to prove. Notice that it is important for our function to be continuous, otherwise the equality may not hold. Okay, so that is the first theorem, the mean value theorem for integrals, which is going to be useful in proving the second fundamental theorem. Next, we will do an example. So this example involves evaluating this integral and showing that this integral is in fact continuous. If you look at this function, and I have done examples like this, so I'm going to go over that relatively quickly. There's some justification that needs to be done. I will tell you what needs to be done. So if you look at this function, it's not a continuous function. It's continuous from 0 to 1, from 1 to 2, but at 1 is not continuous. However, if you look at its integral, it ends up being in fact continuous. So f of x becomes, or I guess capital F, integral from 0 to x of 1 if x is from 0 to 1. Since f is continuous on 0, 1 and bounded. So by a theorem, the value of the function doesn't depend on the endpoints. And that means f of x would be just x. We could just evaluate that. If x is from 1 to 2, then we would have to apply the same theorem. And an exercise that tells us if something is integrable over two intervals, then it would be integrable over the entire interval, and additivity. So this is the part that needs to be justified. To obtain f of x is equal to integral from 0 to 1 plus integral from 1 to x. Now, integral from 0 to 1 is just 1, is just f of 1, which is just 1, plus integral from 1 to x of function is x plus 1, so it would be t plus 1 dt. And then we can apply the first fundamental theorem. So it would be x squared over 2 plus x minus 1 squared over 2 plus 1. And we could simplify this. So it would be x squared over 2 plus x minus a half. Since this function t squared over 2 plus t is c1 on the entire real line. So we can apply the fundamental theorem of calculus, first fundamental theorem. Therefore, we get our function. We get f of x is equal to x if x is between 0 and 1, and if I add 0, I cannot really define it because it's integral from 0 to 0. That's not something we have defined. We will define it later, but we haven't defined it yet. And if it is between 1 and 2, it would be x squared over 2 plus x minus 1. Now it's clear that this function is continuous from 0 to 1 and from 1 to 2. At 1, you will have to show the continuity from the right and left, and that's like one of the exercises, that if you have the limit from one side and limit from the other side, if those are the same, then the function, the limit overall would be this common value. Okay, so next we are going to prove this, in fact, in general, that why is it that integrals are always going to be continuous regardless of what the integrand is. Suppose f from ab to r is integrable, then capital F from ab to r defined by f of a equals 0 and f of x equals integral from a to x is Lipschitz, and therefore it is uniformly continuous. If you look at what this tells us, if you look at the area underneath the graph of the function, if you change your x value, the value doesn't change by a whole lot. It changes by a maximum of, if you go from say u to v, it changes by a maximum of v minus u times the height. Let's say a is something more than the function. So this is the maximum change, which is why it is Lipschitz. Okay, so let u and v be inside the interval from a to b. Suppose u is less than v. If you take the difference of these two, f of v minus f of u, this is going to be equal to integral from a to v of f minus integral from a to u of f. Integral from a to v by additivity is integral from a to u plus integral from u to v minus integral from a to u of f by additivity. And that is equal to integral from u to v of f. So that means absolute value of f of v minus f of u, which is absolute value of integral from u to v of f, by a theorem, this was, I guess we call it a corollary, is less than or equal to integral from u to v of absolute value of f. However, we know that f is bounded because f is integrable. Since f is bounded, there is some a in R such that absolute value of f of x is less than or equal to a for every x in the interval from a to b. By monotonicity of integrals, integral from a to u to v of absolute value of f would be less than or equal to integral from u to v of a, and that is a times v minus u. Therefore, if u is less than v, then absolute value of f of v minus f of u is less than or equal to a absolute value of v minus u. And it's the same when u is greater than v, then absolute value of f of v minus f of u is the same as absolute value of f of u minus f of v. And if you apply the exact same thing, we get this, which is the same as a times v minus u. And if u and v are the same, if u is equal to v, then they're both 0. F of v minus f of u is 0, and so is a times absolute value of u minus v. Therefore, f of v minus f of u is always less than or equal to a times v minus u for every u and v inside the interval. And that's exactly the definition of Lipschitz. So that means f is Lipschitz. And every Lipschitz function is uniformly continuous, as you have shown in your in an exercise. Okay, finally we get to the second fundamental theorem. So what is the second fundamental theorem and how do we prove it? Suppose a function f from ab to r is continuous, then the derivative of this function is the integrand. Derivative of integral is integrand. Okay, so I'm going to take a point inside the open interval and I'm going to show that the derivative is in fact that value. So let f of x be the integral from a to x of f for all x inside the open interval. And let x naught be in the open interval. If you look at f prime, that's the limit of f of x minus f of x naught divided by x minus x naught. Now, numerator is in fact integral from a to x of f minus integral from a to x naught of f over x minus x naught. So there are two possibilities. If x is more than x naught, then integral from a to x of f is going to be integral from a to x naught of f plus integral from x naught to x of f. And if x is less than x naught, then integral from a to x naught of f would be integral from a to x of f plus integral from x to x naught of f. The first case implies that fraction integral from a to x of f minus integral from a to x naught of f over x minus x naught is equal to integral from x naught, because x naught is smaller, to x of f over x minus x naught. And the second one tells you integral from a to x of f minus integral from a to x naught of f over x minus x naught is going to be, if you negate the denominator, you get x naught minus x. Negating the numerator, you also get integral from x to x naught of f. So, in both cases, we can apply the mean value theorem. So, in both cases, by the mean value theorem for integrals, there is some c of x between x naught and x such that this fraction, which was f of x minus f of x naught over x minus x naught, is equal to lowercase f of c of x. So in both cases we have that. Now notice that since c of x is between x and x naught, so this means limit of c of x as x approaches x naught is in fact equal to x naught, because c of x is between x and x naught. So that means the limit as x approaches x naught of f of c of x is equal to f of x naught, since f is continuous. And what was the limit of this when x approaches x naught? That's exactly f prime of x naught. Therefore, capital F prime of x naught is equal to lowercase f of x naught. And that's the end of the proof here. So derivative of integral becomes integrand. Okay. Finally, we are going to do an example on derivatives of integrals. So if you go back and look at the second fundamental theorem that we just proved, it requires the function, the integral, to have a constant lower limit of integration, and the upper limit of integration is the one that is changing. So the constant is at the bottom. What happens if the constant is on top and the bottom is changing? What happens is the derivative is going to be negative f of x. So here's what we're going to do. If you look at the integral from x to b of f, by additivity, this is the integral from a to b of f minus the integral from a to x of f. This follows from additivity. Now take the derivative. Derivative of integral from x to b of f is equal to derivative of integral from a to b, that's just 0. Negative can be taken out, and derivative of this is exactly f of x. This is by the second fundamental theorem that we just proved. So therefore the derivative of integral from x to b becomes negative f of x. So today we talked about the mean value theorem for integrals. We proved that, and then we used that to prove the second fundamental theorem. And that brings me to the end of this video. Okay, so if you would like to continue with these videos, with this class, feel free to subscribe, and I will see you in the next video.